Hello, everybody. It's time to relate the size of a telescope, how big the telescope is, to how bright it makes images. What we really have to pay attention to here whenever we talk about the size of the telescope is, what do astronomers mean by size of the telescope? We mean the diameter, the edge-to-edge length of, say, the primary mirror, and then how that relates to the surface of the mirror, which is doing all the light collecting. Let's go ahead and dive into the video. And if you're interested, this is in the main part, or this is in the lecture notes. This is just all of the telescopes, all the large telescopes in the world, the largest ones, some in existence, some have not yet been built, and just size comparisons, because size is going to be the thing that we want to make as large as possible when it comes to telescopes, because telescope size relates to image brightness. Let's try to walk our way through there. But before we do that, just to make sure we're all on the same page, because not everybody remembers all their geometry, and because telescope mirrors are usually circular in shape and lenses are circular in shape, let's review some terminology related to a circle. So, whenever astronomers talk about the size of a telescope, we're referring to the diameter of the telescope. An example would be the upcoming Vera Rubin Observatory is going to be an 8.4-meter telescope. That's whenever I talk to people about this and I introduce it, or people ask me about it. Hey, have you heard about the Vera Rubin Observatory? Do you know how big the mirror is going to be? And I'll be like, oh yeah, it's an 8.4-meter telescope. So that's how we refer to it. Whenever we say 8.4 meters, we're referring to how big the primary mirror is, not the physical size of the whole telescope itself, the size of the primary mirror. So whenever you hear people say telescope size, they're really talking about the telescope diameter. I might want to talk about, say, the Apache Point 3.5-meter telescope. I know that telescope has a primary mirror of 3.5 meters. A 1-meter telescope has a diameter of 1 meters. An 8-inch telescope has a primary mirror that's 8 inches from side to side. All right, so now that we have how we talk about telescopes, the size of telescopes down, let's go ahead and review our geometry of a circle. So here I have a nice circle drawn. And remember that the diameter is from one edge of the circle through the center of the circle to the other edge. That is the diameter of the circle. The radius of a circle is from the center to the edge. So notice that the radius is half the diameter. So the radius is equal to the diameter divided by 2. Not so bad, just to remind ourselves, whenever I say diameter, I'm talking about the edge to edge length going through the center, and the radius is from center to the edge. And 2 radii equals 1 diameter. Okay, now that we have that, let's actually talk about how telescopes are going to be gathering up light. You can almost think of a telescope as a giant light bucket. Hang on a second, I got a little mini bucket right here. So as light is coming down, it enters the tube of the telescope and it goes down and it hits the mirror at the bottom. So the mirror at the bottom right there is that's the size that's being collected. That's where all the light is hitting. So the light is going to come down into the tube of the telescope, our light bucket, and all the light that hits the mirror is going to be gathered up and focused to make a brighter image. So we really care about the entire surface area of the mirror, because the entire surface area is gathering up the light. How big of a surface is it? Just like if I had a small bucket and a big bucket, and I went out and put them in a rainstorm and waited an hour, after 1 hour in a rainstorm, the big bucket, the one that has a bigger opening, will have collected more water. Okay, so it is the surface area of the mirror that matters, which means that we have to talk about the area of a circle. Now, the area of a circle is one of those equations that I highly recommend, if you do not have committed to memory, commit it to memory. The area of a circle is equal to the number pi times the radius of the circle squared, pi r squared. And pi right here is this long number right here, which is an odd number in nature. It's so-called transcendental number in nature, one of many transcendental numbers in nature. And it is the ratio of the circumference, the distance around the circle, to the diameter. So the circumference divided by the diameter for every circle in existence equals pi. And that's where the number pi comes from. It's simply the ratio of the circumference to the diameter of the circle. Something a little extra for this video. And it comes up everywhere in nature. Anytime you're in a science class, you're going to be talking about the number pi. You do not have to memorize what it is going out to. Just don't do like Indiana did once and try to declare pi to equal 4. Pi equals 3.1415925 dot 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 for onwards and forever. It has no end. You can keep adding another decimal place forever. Okay, so now that we know that the area of a circle equals pi, a number, times the radius of the circle squared, we know the entire surface area of a mirror that's going to be collecting light. And since this area, that's what's doing the gathering of the light, and that's good, and more light equals brighter, right? If we have 10 times more light coming at us, that would be 10 times the brightness. Therefore, whenever we talk about the area of the primary mirror, the surface area, it's usually referred to as the light gathering power of a telescope. Gives you an idea of how much light the telescope can gather. So that it's really just a fancy way that astronomers refer to the area of a telescope. It's the light gathering power, sometimes referred to as the light collecting area. Okay. So how might we want to work with this? It's always good to compare one scenario to another scenario. So we'll compare one telescope to another telescope. And what I really want is I just want a quick and easy way where I can very mentally come up with, if I say, hey, here's two different telescopes, how many times brighter does the large telescope make images compared to the small one? It's the same thing as saying, how many times greater is the light gathering capacity, the light gathering power of the bigger telescope compared to the smaller telescope? And the way that we can do that is we can just take the ratio of the two. The ratio of the light gathering power between two telescopes is going to give us the ratio of how bright they make images. And it's really just going to be a ratio of their sizes squared. And size could be by the radius or by the diameter. So let's go ahead and take a look at how you can come to what's going to be something pretty easy to work with. So I want to figure out the light gathering power of, say, this big one compared to this small telescope, this big mirror compared to this small mirror. This big one has an area of pi times its radius squared, and I'm just calling this one the second one, so R2 squared. This one has a area of pi R1 squared, pi times its radius squared. So let's just look at the ratio of this one compared to this one. So the ratio of the areas, area 1 divided by area 2, that's what the ratio of the areas means, would be pi R1 squared divided by pi R2 squared. Notice that the pi's are just going to cancel out. Pi divided by pi is 1. And then I can simplify, and I get that the ratio of the areas equals the ratio of their sizes, their radii, squared. Because R1 divided by R2 is the ratio of the telescope sizes. Works for diameters too. And if I double the radius, I double the diameter. Okay, hopefully that wasn't too confusing to follow along with. Let me show you how easy it is to actually realize that the ratio of areas is the ratio of their sizes squared. Because when we're talking about light gathering power, how many times brighter does one telescope make images compared to another one? Let's run through some examples. So let's say we have telescope A. I'm really creative in my naming today. Telescope A is 5 times bigger than telescope B. Maybe telescope A has a diameter of 2 meters and telescope B is a 10-meter telescope. It's 5 times bigger. Maybe telescope A is a 5-inch telescope, and telescope B is a 25-inch telescope. Telescope B would be or sorry, I've been doing that backwards this entire time. Uh, Telescope A is a 25-inch telescope, and telescope B is a 5-inch telescope. So telescope A is 5 times bigger than telescope B. Or maybe telescope A is a 5-meter telescope, and telescope B is a 1-meter telescope. Telescope A is 5 times bigger than telescope B. So just the ratio of their sizes. Well, A is 5 times bigger. That's the ratio of their sizes, and therefore would make images 5 squared, the ratio of their sizes, 25 times brighter than telescope B would. Because that is 25 times the light gathering power compared to B. So it makes images 25 times brighter. And doesn't have to be nice, easy numbers like 5. It could be something like telescope C is 7.5 times bigger than telescope D. So telescope C is a 15-meter telescope, and telescope D is a 2-meter telescope. Telescope C is a 7.5-meter telescope. Telescope D is a 1-meter telescope. The ratio of their sizes, telescope C is 7.5 times bigger than telescope D. Okay, so how many times brighter will telescope C make images compared to telescope D? How many times larger is telescope C light gathering power compared to telescope D? It's just the ratio of their sizes, 7.5 squared. So 56.25. So telescope C has 56.25 times the light gathering power that telescope D does. That is, it'll make images 56.25 times brighter. So small increases in telescope size translate to a huge gain in how bright images are. And remember, we want to be able to see the faintest things in the world. So we really, really, really want super large telescopes. And just by doubling the size of a telescope, we are now going to make images 4 times brighter. We can access a lot more of the universe. All right, and just to show you that all the math does work out, I'm just going to quickly go through all of this. So here I have 3 different telescopes. This one is a 0.25 meter telescope, a 25 centimeter telescope. This one's a 1-meter telescope, and this one is a 2-meter telescope. So I could go ahead and I could crunch out their light gathering powers. I could crunch out their areas by doing pi r squared, and I could go ahead and get these numbers right here. Notice that pi is always going to be there, and I like using just pi because it's exact. So the area is 0.0625 pi meters squared. Do the same thing here. So pi r squared, pi times 1 squared is just pi meters squared in size. And this one over here, pi r squared, pi times 2 meters squared, that's 4 pi meters squared. If you really want to crunch the numbers, you're welcome to crunch the numbers. Now I want to compare the light gathering power of this telescope to this one, and this telescope to this one. So telescope 2 to telescope 1. Let's go ahead and have a look. Let's first just calculate the ratio of their sizes. All right, so this telescope is a 1-meter telescope. This telescope is a 0.25 meter telescope. 1 divided by 0.25 is 4. Telescope 2 is 4 times bigger than telescope 1. As we did on the previous slide, I could come up with my answer. I could take the ratio of their sizes, 4 squared, 16. Would have 16 times the light gathering power compared to telescope 1. It would make images 16 times brighter than telescope 1. Or if you actually want to see that all of this work right here, I was able to do everything just symbolically, algebraically, with never having to really use the real numbers. But you could use the real numbers. What is the area of this telescope? Pi meters squared. What's the area of this telescope? 0.0625 pi meters squared. Pi divided by 0.0625. Those cancel. The pi's do. Pi divided by pi. So 1 divided by 0.625. Put in your calculator if you don't believe me. 16. Same answer. I'd rather just look at the ratio. Hey, it's 4 times bigger, square, 16 times brighter images with this bigger telescope here. That's quick, fast, and easy than if I were to make you run through the calculations, calculate the light gathering capacities, and then compare them. All right, so let's do it with the biggest one, our 2-meter telescope, compared to our 1-meter telescope. What is the ratio of the sizes? Well, this telescope right here, telescope 3, is a 2-meter telescope divided by the size of the 1-meter telescope, a 0.25-meter telescope. This telescope is 8 times bigger, and now you can clearly see that has a heck of a lot more area than this one does. So it's 8 times bigger. So how much brighter will this make images? Oh, ratio of the sizes squared. 8 squared is 64 times brighter images. 64 times the light gathering power. Or you could actually crunch out, calculate, and compare the areas. This one has an area of 4 pi meters squared. This one has an area of 0.0625 pi meters squared. So 4 pi divided by 0.0625, the pi's cancel. 4 divided by 0.0625 would equal 64. Notice that is just 4 times what it is over here. 4 times 16 is 64. Oh, nice. This one's 2 times bigger. Telescope 3 is 2 times bigger than telescope 2. 2 squared is 4. Oh, it all works out. It all works out just by thinking proportionally. And the final thing I'd like to run through about what is one of the biggest benefits of making images brighter, other than being able to capture the faintest objects in the universe and being able to observe them. Even with those, we usually have to take a telescope and stare at something for a very long time, just letting more and more light come to us, keep the shutter open and just keep exposing. But that takes a large amount of time. To do observations of faint objects, you might have to spend 9 hours at the telescope staring at some faint star to get the quality of data that you need to do the science that you're after. So let's imagine that we are one of those scientists, and let's use those numbers that I was just saying. So imagine that you are trying to do some groundbreaking work on a type of star, a rare type of star, but the closest one to the Earth is very, very, very dim in the sky. You only have access to a 1-meter telescope, and you know that to get the amount of data that you need, it takes you 9 hours of observing that star. So 9 hours of observing to get that one data point that you need. That's a lot of time, 9 hours. That's a lot of time for something to go wrong, and maybe you have to throw out the entire observation. What you'd really like to do is get the same quality science in a much shorter time. So, being frustrated of wasting your night after night, all 9 hours observing the same thing, you propose to do an observation with a bigger telescope. And yes, you get awarded some time on big telescope, that's the name of it. That is you get awarded time on a 3-meter telescope that's 3 times larger than the small telescope. So now you have access to a bigger telescope. The big telescope is 3 times bigger, which means that it's going to make images 9 times brighter than the small telescope. Another way to think about this, if you're getting 9 times the amount of light, that means that you could get that same quality data that you need to do your science on this rare star type. It'd take you 1/9 the amount of time to get the same quality data. It'd take you 1/9 the observing time, 1/9 the exposure time. So instead of staring at a star for 9 hours every night, you could use 1 hour of observations to get the same quality data that you need. And now you have an extra 8 hours free. What are you going to do with all that extra time? Maybe you're going to observe more stars. Maybe you're going to take a nap. Maybe you're going to use that time for whatever you want. Astronomers are going to make use because now they have so much more time to do more observations and learn more about the universe. So, a quick recap: telescope size determines how bright a telescope can make images. And the brightness goes with the size of the telescope squared, because you're talking about the area of a circle, and that has a size squared component. So you get a big bang for your buck by making a telescope a little bit larger. You make images a lot brighter pretty easily. And it's not only at this point that you can just make images brighter so you can see fainter things, but you can also do something a little bit practical and reduce the amount of time that you have to spend observing every single object. You can use a bigger telescope to observe more things in a single night. So you can really make use of your time at a telescope. All right, so I don't really quiz you on exposure time, but I wanted to go ahead and connect all of that in because it really helps ground this material. I hope you enjoyed this video, and I will see you in the next one.